Okay, good morning, everybody. I just turned on the recording, so we're now recording. And today, let me pull up slides for today. There's something in the chat. Let's see. Oh, okay. Thank you for telling me, Julia, that you have actually watched. Yeah, I do record at my office hour, and so it's available. I'm glad to know that Julia's been seeing it. I hope if people want to, it's available to you. You can see it. Do you see the PowerPoint?
Yep, we see it.
Okay. So I'm going to go into presentation mode now. There we go. Okay. All right. So I guess you haven't had lecture on this material, right? So I'm going to try to pack a lot into today. All right. So chapter 25 is optical instruments. The most important optical instrument is, of course, the eye. So let's talk about the eye. So the eye has naked eye near and far points. So this is, the near point is the closest distance at which you can focus on an object clearly. And you can just do that yourself, figure out where you can do that. The far point is the farthest distance, the opposite, right? And when you are, there's general consensus of what normal is. So normal is that your near point is about 25 centimeters, something like this. Far point should be infinity. And not everybody has these near and far points. I, for example, don't. Mine is terrible. I can see pretty well about here. That's more or less a normal near point. But the far point is just lousy. About that's my far point. Beyond that, it just gets blurry. So instead of being infinity, it's this. That's why I wear glasses. Okay, we will be mentioning, the book mentions a lot, a relaxed eye. The meaning of a relaxed eye is that it's focused on infinity, which the implication then is if the eye is not relaxed, you're focused somewhere closer to infinity. So for example, you can focus on your near point by pulling the muscles in your eyes, and that changes the lens. And you can't focus any closer than that, just by definition of what the near point is. You can strain, but it won't work. Okay. Now, when you want to scrutinize something, what do? You want to look really carefully at the details. So if you hold it away at a certain distance, like this, your lens and your eye will put an image on your retina, and that's how you can see it. Excuse me. But if you really want to scrutinize it, if you're looking at like the letters on a coin or whatever, what do? You move it closer to your eye. So here is the same object, closer. And you can see that as a result of it being closer, the image on your retina is now bigger. And that's why you can see it, the details, better. And so how large an object appears and how much detail you can see in it depends on the size of the image that it makes on the retina. But of course, if you bring it too close, then you can't focus on it anymore. And so what do you do if you move it to your near point and you still haven't been able to resolve the details that you want to? You pull out a magnifying glass. Magnifying glass allows you to put the object even closer to your eye than your near point, because what it does is it creates an image, a virtual image of the object, and puts the image far away from your eye. So magnifying glass, the lens of a magnifying glass puts the image, the virtual image of the object. You see, it's a virtual image, right? Here are the rays that come out of the object, but this person infers that they came from way back there, so the image is over here and it's virtual. The lens puts that image farther away where you can focus on it. And so that's why you can scrutinize the details on it. And also, you have a magnified image. So you can place the image at the near point, right? That's the best you can do in terms of scrutinizing it, right? So the object will be, here I'm looking at my thumb, the object will be quite close to my eye, then I can't focus on it, but then I put the magnifying lens and now I can focus on it. What I do is I adjust it like this, and I have it focused on the near point. Rather, I put the image at the place where the closest point that I can focus my eye, the near point. That's one thing that you can do. And there's the near point. Notice that the near point is the distance from your eye. That's an important thing. Another thing you can do is place the image at the far point. And what you do is you take the object, and here you have it between between the focal point and the lens. The object is between the focal point and the lens, and he creates this image. And the closer the image gets to the focal point, the larger the image is and the farther away it is. So if you put the object at the focal point of the lens, on the other side of it, then the image is at infinity. And so you can do that. You can arrange things that way. Then you can have a relaxed eye, have it focused on infinity, and then see the object that way. Okay, so now we can talk about angular magnification, or magnifying power. This is often how such things are described. It is not quite the same as the magnification that we've had before, which was just the ratio of the image height to the object height, but is related. Angular magnification is related to the angles subtended by the object and the image. Sorry, my voice is really heavy today. Okay, so what do I mean by this angular, the angle subtended by an object? So here's an object held at the normal close focus point, N, to the eye. And you can see the object is a leaf here, has a certain height and is a certain distance away from the eye, so we can figure out what this angle theta is. The tangent of theta is h over d. Now, these are typically very small angles. Right? We have a tiny leaf and it's 25 centimeters from the eye. So it's a tiny angle. And we can do an approximation for the angle and just say that the tangent of theta is about equal to theta. You might remember that the sine of theta is about equal to theta for a small angle, and the cosine of theta is about equal to 1 for a small angle. So then the ratio is just theta. So we'll use that approximation. Now, with a magnifying glass, as we were saying, the object you can place it closer to your eye. And so then the image then is big and it subtends a larger angle than the actual object did. You have this situation. So now the object is closer to the eye, but you're not looking at the object, you're looking at the image of the object, which is farther away. And so you see this is a different angle, theta prime. So how are we going to figure out angle theta prime? Well, look at this right triangle here that I've highlighted. That angle is theta prime, and you can see that it's h over the object distance. And again, these are small angles, so you can approximate that to be about theta prime. Instead of tangent theta prime, it's about equal to theta prime. Okay. All right, so then angular magnification, or magnifying power, is the ratio of these angles. So we had this angle, h over n, for the angle theta. That's looking at the object without the magnifying lens. And then with the magnifying lens, we had the angle theta prime, which was h over the object distance. So we can plug those ratios in up here, like this. Those h's cancel out, and we get n over d0. Okay, so n is the near point, so by default, or by definition, 25 centimeters. Unless you're talking about a specific individual that has a specific near point, we'll use 25 centimeters for n. And then d object is the object distance, where you put the object. That's what I said before. Okay, now you might want to express m in terms of the focal length of the lens, so that you don't have to have the magnification depend on where you put something, right? Because you can adjust it. So case number 1, these are the two cases I mentioned before. Case number 1, your eye is relaxed, meaning that it is focused on infinity. So you can arrange the eye, the lens, and the object so that the image is at infinity. That's this picture that we had before. That means that the object then is at the focal point of the lens. So this focal distance is equal to the object distance. So we can just plug that in there. D0 equals f. So our magnification becomes n over f. And that's good because then that magnification doesn't depend on where you choose to put the thing. However, we are assuming that you have a relaxed eye. That, by the way, is this equation. And I wanted to clarify these equations because when I read it, I found it very confusing. So I'm breaking down these equations for the magnifying lens. All right, so that was case number one. When you arrange things like this and you have a relaxed eye, the image is at infinity. The other case that we mentioned was you could focus your eye in the near point and have the image at the near point. So you arrange the eye, the lens, and the object to put the image at the near point. So that means that the image distance is equal to the near point. That was this situation here. Okay, so now we can get the object distance from the lens equation. So for the image distance, we've got the near point, because that's where we put the image. And the object distance, excuse me, the focal point is f. So we can take this and we can solve it for d0 and stick it in the equation up here. And then we get this. Right, so the image distance, notice, by the way, I want to point out the image distance is measured from the lens. So remember, all the image distance, object distances, they're measured from the lens. Near point and far point is measured from the eye. And there's usually a distance between the lens and your eye, right? So you have to take that into account when you calculate these things. Okay? So with some algebra, we're able to express the magnification this way for the situation where your eye is focused at the near point. That's equation 25(2)b. Okay, a little more words about the eye. A nearsighted eye, the problem is that the objects at infinity focus in front of the retina rather than on the retina. And this is the case for me. So I see my finger just fine, like this, but when I look at something very far away, it's a blur. It's a blur because the image inside my eye is in front of my retina. So what do is I get my glasses, which correct my vision. Here they are. And they're this kind of a lens, a diverging lens. It takes these parallel rays which come in from something really far away, makes them diverge a little bit, and then the lens does its trick. And then with the combination, the image ends up on my retina and I can see clearly. So to correct nearsightedness, you use a diverging lens like this. Okay, so let's work something out. An example. I'm going to go through example 25(6), which is in the book, but I want to clarify things along the way. So we are assuming we have a nearsighted person whose naked eye far and near points are 17 centimeters and 12 centimeters. So that's the range in which he can see things in focus. So you can see that's pretty impractical, especially this far point. Things that are far more than 17 centimeters are just a blur to this person. And I can relate. So what we want to do is pick out a lens so that an object that's infinitely far away has its image placed at the far point, like this. Right? So the object is infinitely far away. This lens will put the image at this location, 17 centimeters from the eye, where the person can actually focus on it and see it clearly. Notice that there's 2 centimeters between the lens and the eye. This is not contact lenses. There's a space here, and you've got to take that into account. Okay, but notice that since the way we're measuring things, the object is over here on this side of the lens, and the image is on the same side of the lens. So we have a negative image distance. The image is formed on the same side of the lens where the light comes in. So the image distance is negative. Again, I want to emphasize the image distance is measured from the lens, not the eye. So the image distance is not 17 centimeters, it's 15. Actually, negative 15 centimeters. 17 minus 2, and then throw the negative sign in for the placement of the image. So in that situation on the screen, the image distance is negative 15 centimeters. Okay, so how strong of a lens do we need? So we can use the lens equation. We now know what the image distance is. It's negative 15 centimeters. And the object distance is infinity because it's infinitely far away. So we plug that into here, and we can solve for f. We get negative 15 centimeters, right? So d0 is infinity, so this term becomes 0, and so f just equals d. So the focal point of the lens is negative 15 centimeters, but we want to know how strong the lens is in diopters because we're talking to an optometrist. So let's convert this then into diopters. So diopters is 1 over the focal length, specifically has to be in meters. So I changed 15 centimeters to 0.15 meters, and we get a power of negative 6.7 diopters. So that's the prescription for this guy. Is there a question?
Comment that says cool.
Cool, yeah.
And then,
Especially cool for people like me who are otherwise blind as a bat.
oh yeah, my near point is worse than yours, or far point, whatever. But I had LASIK. And then the other question is, do the far and near point not follow the same sign conventions for object and image distance?
Correct. Near and far points are just plain positive distances. And because they're not images, they're not objects. Near and far points are just distances that you measure from the eye. Okay?
Yep. Thank you.
Okay, good. All right, now remember, let's go back and remember what this guy's near point, I don't remember, it's 12 centimeters. So this person's naked eye near point is 12 centimeters. That gets messed up when he has his glasses on. So what is the corrected near point? So corrected meaning with the glasses on. To answer that question, where would you put an object so that the glasses put the image at the naked eye near point? Right, so the lens, there's the picture. Here's the object. Where is that so that the image created by that lens is at the near point of the person, right? So the person can actually focus on it. Okay, so you see that's a positive 12 centimeters because it's a distance measured from the eye. The image distance is, the object distance is positive and the image distance is negative. There we go. So, and this was 2 centimeters. I forgot to put that in there. Remember from the previous slide, it was 2 centimeters from the lens to the eye. So the image distance is then negative 10 centimeters. Right? 12 minus 2, and then throw in the negative sign because the image is on that side of the lens. And then we already figured out that the focal length of the lens is minus 15 centimeters. All right, so we can find the object distance with the lens equation. Plug those things in and do some algebra. I will spare you the algebra. The answer is 30 centimeters. So the corrected near point is 32 centimeters from the eye. Remember, there's 2 centimeters here. So now the person with the glasses on can't focus on the object as close to the eye as he could before. It has to be a little bit farther away. And I can demonstrating this is meaningless because it's subjective. But look, so without my glasses, I can focus on my thumb about there. That's my near point. Put on my glasses, and no, I can't focus on it anymore. I have to take it further out. That's about 30 centimeters or so. So it's more or less what's going on there. Okay. So wearing glasses changes your near and far points. The idea is to put things that are far away, put the image of things that are really far away at your far point so you can focus on it. And then as a result, the corrected near point changes. The far-sighted eye has this problem, and that is when an object is nearby, it focuses behind the eye. Right? So something far away can look reasonably clear, but as it gets closer, the image gets focused behind the eye, and so it's blurry. Right? The image actually on the retina is blurry. So you can correct that with a converging lens like this. Make the light rays bend in a little bit, and then they end up putting the image right in your eye. So there's an example on 25.5, which is an example immediately preceding the one I just worked out. That one's quite straightforward, and in the interest of time, I'll just refer you to page 720 for that and go on. So to correct far-sighted vision, that's a converging lens. And remember, converging lenses look like magnifying lenses, or act as magnifying lenses. So, sometimes you see people wearing glasses and their eyes happen to look bigger when they have the glasses on. That's because they're farsighted. All right, let's talk about telescopes, other optical instruments. So use telescopes to look at things that are really, really far away, of course. But before talking about that, let me remind you something about converging lenses. So this is the picture that you always see for a converging lens. You have light rays coming in parallel to the axis, and they get focused on the focal point. But converging lenses do more than that. If you've got parallel rays coming in that are not parallel to the axis, they get focused on the focal plane somewhere away from the axis, like this. Right? And similarly in the other orientation, of course. Right? So that way, this lens forms an image, of if you have an object that's infinitely far away, the image is formed on the focal plane, not just the focal point. Okay, so with that, let's now consider a refracting type telescope. And it consists of two lenses. So let's pay attention first to the objective lens, which is one that's farther away from your eye. And we're pointing it towards something that's infinitely far away. And so some light rays come in from the top of the image. And the image of the top of the object gets formed over here on the focal plane. So this is the focal distance of the objective lens, so FO. FO is the focal distance. Yeah, FO. Okay, so lowercase FO is the focal distance. Capital FO is the focal point there. And that's a distance, lowercase FO, away from the lens. Okay, now what? So we have this image formed at this location nearby, rather than being infinitely far away, it's here. Now what do? Well, we basically put in a magnifying lens to look at that image. And that is this eyepiece. So the objective lens creates this real image there, and then we look at the real image with the magnifying lens, which is the eyepiece. And so the eyepiece then magnifies that image and puts the image over here. And that's how this type of telescope works. There are other kinds of telescopes that are described in the book. I just want to concentrate on this one. So notice something. For this to work as well as possible, the object is infinitely far away. So the image that's formed is basically at the focal point of the objective lens, FO. In order to magnify that as much as possible, we arrange the eyepiece and our eye so that that image is close to the focal distance of the eyepiece, and that's FE. If we put FE right on, if we move the eyepiece around so that the focal distance of the eyepiece is right on this image, then the image here is infinitely far away. You can look at it with a relaxed eye. So ideally, and with a relaxed eye, the length of the telescope, which is the distance between the objective lens and the eyepiece, is just the sum of the focal distances of the objective lens and the eyepiece. And so in this diagram, there's this little distance here, which is not quite zero. So ideally, you can move the lens a little bit farther away so that the image is right on that, and then this first image is right on the focal point of the eyepiece, then the image formed by the eyepiece is very far away. So basically, you just move it back and forth to try to get that as close as possible and still be able to see it clearly. So this is sort of the idealization then of a telescope, the length of a telescope.
When you're adjusting the telescope, you're really adjusting the magnifying glass?
The eyepiece. The eyepiece is going back and forth when you're focusing it.
Okay.
And the eyepiece is the magnifying glass. That's basically all it's doing. You're using that to look at the image that's formed by the objective lens. Okay? Yeah, so whenever you read the length of a telescope, that means the distance between the objective lens and the eyepiece. Of course, that's housed in a big tube, and the tube itself is longer than that. So then, that could be confusing, but the length of a telescope is defined as that distance. Okay, and then the magnification is, the angular magnification is then the ratio of these two angles, right? So there's the angle theta prime that subtends the image that you look at. The angle theta is what subtends the image of the object, or rather, the first image of the object here. And I'm just going to quote the equation here. It's minus FO over FE. That follows from looking at triangles on this diagram. It's not that hard to do. You look at this triangle here, and then that triangle there. But I'll spare you the details and just refer you to that equation 25.3 in the book. So we'll use this, that the magnification is this. Notice that there's a minus sign in there. Minus sign there is there because, well, the image is upside down. The first image is created upside down. The eyepiece doesn't flip the image. So the overall thing is upside down. That's why there's a minus sign. And this can cause some confusion, because sometimes you look at telescopes and their magnification is quoted as a positive number. It's really a negative number, but people ignore it because, if the moon is upside down, it still looks like the moon. It's not like you're looking at a person, where looking at a person upside down is really very counterintuitive. So you can either use this formula and realize that the magnification is a negative number, or treat the magnification as a positive number and use this formula without that minus sign. That can cause some confusion. Okay, let's go on and talk about a microscope, which is basically the same thing, except that the things are arranged a little bit differently. In this case, the object is close. Instead of being infinitely far away, it's close. It's here. And there's the objective lens. As a result, the image formed by the objective lens is over here, far away from the focal point of the objective lens. It's inverted still, like that. And then once again, you put an eyepiece here to use as a magnifying lens to look at this image. It is. That puts the image way over there in a nice magnified form. So that's why the microscope works. Right, so the big difference between the telescope and the microscope is just that for a telescope, the object is infinitely far away, and for the microscope, the object is close by. Still farther away from the objective lens than its focal length, but still pretty close by. Okay, so the magnification of a microscope is then calculated as the magnification of these two things. First, by the objective lens, because you see there's the object, this image is bigger. Excuse me. And then the magnifying lens magnifies it. So what is the magnification of the objective lens? Well, that's our old equation that we had from before. I-ho equals minus dido. But let's ignore the minus sign, because again, the minus sign simply means that you're looking at it upside down. We don't know our paramecium friends well enough to know if they're upside down or upside up. So I'm just going to write it this way and quote it as a positive number. Is there a comment?
Yes, an LOL.
Paramecium friends, yeah.
And then it says, that's amazing, but doesn't our brain switch the inverted image?
Well, no. If you use a microscope to look at a person, the person will be upside down. Assuming the person is right side up and you put the microscope there, it'll be upside down. And maybe with a telescope is a better example. So maybe the telescope that you're more familiar with is not this kind of a refracting telescope. It's got another piece in it that flips the image. This is right. So that kind of this kind of a telescope is maybe not the typical one, because the typical one will have another image lens which will flip the thing back over again. Right? But this is the simplest one to discuss in the class. So I'm going to clarify that before I post these slides. Thank you for bringing that up. All right, but now let's calculate the magnification of the microscope. The objective lens, we use this old equation and ignore the minus sign. Now notice that the image distance, here it is, it's the distance of this image to the objective lens. And it is the length of the microscope, which again is defined as the distance between the objective lens and the eyepiece, minus this focal distance of the eyepiece. And again, to get the largest magnification out of the eyepiece, you move it back and forth until this image is very, very close to the focal point of the eyepiece. So in this configuration, the image distance is there, di. It is the length of the microscope minus fe. That's what I wrote down here. Okay? Plug that in up here, and we get that the objective lens magnification is this, L minus fe over d0. Okay, so let's just hold on to that. Now the magnification of the eyepiece, well, that's a magnifying lens, and we already figured that out before for the case where you have the relaxed eye, right, N over fe. So now we can multiply these two things together. And if it so happens that the focal length of the objective lens and the eyepiece are small relative to the length of the lens, which is what you do with the microscope, this quantity can be approximated this way. Okay, so both these equations are on page 726. You can use either one of them. So magnification of the compound microscope in terms of the length of the microscope, the focal length of the eyepiece, object distance, that's this distance there, N over fe. So that may be not so convenient because maybe you don't know what the object distance is, depends on how you use it. But if you arrange it this way, then this approximates to this more or less, assuming this thing here. Okay. All right. So now let's talk about limits of resolution. And this gets into diffractions. So if you have a lens and you have an aperture, you have diffraction. Before we were talking about diffraction forming from a little slit in a screen, right? And basically we were thinking about things in 2 dimensions. We drew it in 2 dimensions. So we had basically plane waves hitting this something that blocks them but has a little opening, and then we have diffraction. In this case, things are happening in 3 dimensions. So you have plane waves in 3 dimensions, and the screen has a circular aperture. You still get diffraction, but it's slightly different. The diffraction pattern on the wall far away looks like this. So this is a circular aperture, and then the light forms a pattern that looks like this. Again, it's got to be a really small aperture for you to observe this kind of effect. But you can readily do this with cameras. Okay, so the intensity pattern of light looks like this. It's very bright in the middle, and then not so bright outside, as you can see. And the location of that first minimum is specifically 1.22 lambda over d. And that's the angular half-width, right? So in other words, I'm looking at that screen, and this angle from this is right to the middle, and this is to the first dark area. That's this angle. Why is it 1.22? That's what gets calculated out when you do this for a circular aperture. Details are not pleasant, and so we'll just give you the 1.22. This, by the way, has a name. This pattern is called an Airy disk, A-I-R-Y. Okay, so this is the image that you get when you have a single point object, and you use a lens that has a circular aperture. you get the same thing as I was saying with plane waves going through a hole, a circular hole. But you know, basically the same situation is take a single point object and put a lens there with a circular aperture, and you'll form this. Yeah, is there a question?
I was just going to ask that question. Is D the distance? So like the distance as you would for like grading, like that?
I should have clarified. Capital D is the diameter of the opening.
Oh, okay. So the
Thank you. I should have said that. The capital D is the diameter of the opening. The lambda is the wavelength of the light that you're using.
Okay.
So it's most clear if it's a single wavelength, of course. Okay. Now, what happens if you use the same lens and aperture to look at two objects that are close together? So you get a blur. And so now we can ask the question about resolution. You know, under what circumstances can we actually identify that we have two objects rather than just one blurry object? And so that's a very subjective thing. But you can, Mr. Rayleigh has an objective way of saying that. So two images are just resolvable when the center of the diffraction disk of one image is directly over the first minimum in the diffraction pattern of the other. Arrange things like this. So here is the brightness from the image of the first object. If the brightness of the image of the second object aligns with this minimum, that is the Rayleigh criterion for something being able to be resolved. Here's the picture more physically. Here are the two objects, small distance apart. Here's the image, the lens forming the image. And here's the bright spot corresponding to the lower one. Here's the bright spot corresponding to the upper one. And notice that this bright one, this bright thing here is aligned with this dark spot there. So that's the condition for, the Rayleigh condition for two objects just being barely resolvable. And so we can figure out what this angle is. And that's what this angle is, 1.22 lambda over t, right? Because we're just putting those two things that distance apart. When you calculate this, you get an answer in radians, by the way. Okay. All right, so let's do a couple of examples in the remaining time. The first one is to just clarify the meaning of this Rayleigh criterion. So two stars 13 light years away, so very far away, are barely resolved by a 55 centimeter telescope. So it's a mirror telescope, but never mind. And we can treat it just as basically this situation. This object here is the telescope. So the question is, how far apart are the stars? We know how far away they are, but how far apart are they one from each other? And so they're barely resolved as being two separate stars by this telescope. Let's assume that we're using a specific wavelength of 550 nanometers, and that this issue of resolution is limited by diffraction. So here's the big triangle, right? L is 13 light years. S is the separation between the two stars that we want to figure out. And this is this angle subtended by that distance. Remember, this is in radians, so that this distance here you could approximate as a portion of the arc length of a circle of radius L. And so that S is about L times theta, theta in radians. The diameter of our lens is of our opening, basically, which is, it says a mirror, but never mind, it's the telescope. So 55 centimeter effective lens diameter. And here's the wavelength that we're using. So the Rayleigh criterion is that this angle should be this number. So we just plug in these numbers. And we figure out that the angle here is this many radians, 1.22 times 10 to the minus 6 radians. Okay, so with that angle, then we can plug it into here to get what this arc length is, or this. And now let's switch to, or no, we are measuring things in light years, right? So L is in light years, or 13 light years. 1 light year is this many meters. So I'm going to hit light years with the radians, and then convert. I didn't have space to convert, so I'm going to convert light years into meters, and then my answer then is 1.55 times 10 to the 11 meters. Okay. Is there a question?
How did you know that S is around or approximate to L times theta?
So remember that from last semester, that's arc length equals radius times angle, where the angle is in radians. This is the definition of what a radian is.
I do not.
What I'm doing is I'm approximating this separation here as the arc length rather than the actual distance in this triangle, of this isosceles triangle. What was in the comment?
Yes, thank you.
Okay, good. Okay, quickly then, actually, let me take a moment and screenshot the attendance because I just happen to remember. So just give me a second here, please. What did you not remember? Oh, the arc length thing?
Yeah, the arc length.
Yeah, a good thing to know. It's the definition of radians. Okay, let's see. Yeah, that's you. Okay. So you still see the PowerPoint, right?
Yes.
Okay. Let's do this one. This is one of the homework problems that I got some questions about. It's a little tricky, and it brings together some of the things that we just talked about. All right. So pointer. Suppose that you wish to construct a telescope that can resolve features that are 5.5 kilometers across on the moon. We want to be able to distinguish two mountaintops that are this far apart on the moon. The moon is 384,000 kilometers away. We have a telescope. The objective lens is 2.3 meters for its focal length, and the diameter is 12.5 centimeters. Okay. Part A is, what focal length eyepiece do you need in order for your eye to be able to resolve objects 0.1 millimeters apart at a distance of 20? I said that wrong. So your eye can resolve objects 0.1 millimeters apart at a distance of 25 centimeters. In other words, we're going to use the telescope to create an image of these two moons, these two objects on the moon. And the image will have the peaks of those two moon mountains 0.1 millimeters apart at a distance of 25 centimeters, the near focus point. Okay, so let's work on part A before going on to part B. Here's the magnification formula, right? We're going to ignore the minus sign, and we're just going to have the eyepiece focal length related to the objective focal length this way. That just follows from this equation, ignoring the minus sign. We could put in the minus sign, but it doesn't really help in this case because we just want these distances. All right, so for the moon, we have this gigantic triangle. We are here. The moon is 384,000 kilometers away, and the mountaintops on the moon mountains 5.5 kilometers away. So the angle subtended by that is theta. And we approximate that this way. It's a small angle, so instead of tangent theta, I have just theta. Now, the telescope will create an image, and we're going to look at that image with our eye. And the image of the two mountaintops we want to be 0.1 millimeters away at least, because when that is the case and you're looking 25 centimeters away, then we can resolve them. Right? That's what it says here. Your eye can resolve objects 0.1 millimeters apart at a distance of 25 centimeters. So this is what's going on in the telescope with our eye. And that's the angle theta prime. So again, it's a small angle, so we approximate it this way. Now we can plug these two angle things into there. Like that. And then we get an eyepiece focal length of this. 0.0823 millimeters, which is 8.24 centimeters. Okay, so we have that objective lens. If we pull out a eyepiece lens like this, then we can resolve features that are 5.5 kilometers across the moon. Okay, and then in the last few minutes here, we can go on to part B. What is the resolution limit set by the size of the objective lens? That is by diffraction. So above, in part A, we weren't talking about diffraction. We were talking about how well your eye can resolve objects. And we were given this information about your eye. In part B, we want to talk about limits set by just diffraction of the lens. Okay, so in part B, I just changed by putting in the word in. Okay. So in part B, we just use the Rayleigh criterion. The wavelength is 560 nanometers. The diameter of the objective lens we're given is 12.5 centimeters, here written in terms of meters. And this is the criterion. Plug in the numbers, and we get this. 5.47 times 10 to the minus 6 radians. So a tiny, tiny angle. Okay, so that's the diffraction limit. That's not too bad, I would say. Okay. Basically, I'm out of time, right? Yeah, I'm out.
Yeah.
But let me show you. Yeah, go ahead. Go ahead.
You have 3 minutes.
Yeah, but I don't really have time to start something and finish it in 3 minutes. So I want to show you what remains in the slides. I've got some examples worked out, which you can look at. So this is one with an eyeglasses thing. A situation, so a guy looks at a newspaper and then you calculate something about his glasses. And then there's another one, that's the same question. And then another question about a refracting telescope, where you can work out some of these things. And then a microscope as well. So these things are in the slides. I can't really do any of them in the remaining time. And I also will post a PDF of these questions and a couple others. Let me show you that quickly. With my written solutions. Sorry?
I appreciate the drawing, because that's one area in which I struggle.
Yeah, the drawing is, that's the skill, exactly. You see the PDF? It says a week of March 30th. Do you see that?
Yep, we see it.
That. We do see it, okay.
Yeah.
So ignore the March 30th, because, you know, that was last semester. And so here are some 5 problems that I work out. One is about a fiber optic, so relating to stuff from last chapter. The glasses one, which is worked out in the slides, etc., telescopes, etc., and my written out solutions, some of which are in those slides. Okay, so I'll end there. If anybody has any questions, please stick around. I can be around until about 10:25. Otherwise, I'll have an office hour tomorrow. What do we say? 3 o'clock, I think. Tomorrow, 3 o'clock, I'll have an office hour through Zoom. I'll post the link. It'll be recorded if you're not able to come. That's it. Have a good weekend. I hope this was helpful.
Very much.
Please let me know if it was helpful. Have a good weekend, everyone. You're welcome. Bye, everybody. Great. Thank you, Julia. Yeah, thank you. Good. Oh, I'm going to stop the recording now.